Bismillahirrahmanirrahim. Welcome to the Electrical Engineering YouTube channel. In this lecture, I am going to move my discussion to the phasor diagrams of a transformer. So, for plotting these phasor diagrams, I first have to show you the equivalent circuit diagram of the transformer refer to the secondary side, which is shown in this figure. So, the approximate equivalent circuit of the transformer can be plotted or can be drawn by shifting this magnetization branch towards the left side as shown in this figure, and by doing so we can add these primary and secondary resistance and reactances in this secondary resistance and reactances simply because these components will be in series, and at the end we will get R equivalent, which is the sum of Rp over A square and Rs, and we will get Jx equivalent, which is the sum of Jxp over A square and Jxs. So this is the equivalent approximate equivalent circuit of the transformer referred to the secondary side. This is the transformed primary voltage and this is the secondary voltage. So we can apply Kirchhoff's voltage law for this equivalent circuit, and by applying that KVL, we can write Vp over A as the sum of this Vs plus Is into R equivalent and plus JIs into X equivalent, because Is is the current which is flowing through these parameters. And we also have defined the voltage regulation of a transformer, which is actually the relative difference of the secondary voltage at no load and the secondary voltage at the full load. So it will be divided by secondary voltage at no load, and we can multiply this by 100 to calculate the percentage. So at no loaded conditions, when there is no load connected at the secondary, all this primary voltage will appear across this secondary terminals, because there will be no current, and due to this reason there will be no voltage drop across these two series parameters. So in that case, Vp over A will be equal to Vs, and this is Vp over A minus Vs at full load divided by Vp over A. So this expression will help us to approximate or to predict the polarity of the voltage regulation for different types of loads. So if we consider the lagging power factor load in the first stage, we can draw the phasor diagrams by considering the secondary voltage as our reference. So this secondary voltage vector is plotted at the x-axis, and we know that Is is lagging the second is lagging Vs, or the secondary current is lagging the secondary voltage because we have lagging power factor load. So this factor corresponds to the secondary current. And if we want to predict the orientation of the voltage drop across this R equivalent resistance, then its phasor diagram will be aligned with this Is vector, because R equivalent is actually a real number, and the direction of Is will also be the direction of ISR equivalent. So this is the direction of ISR equivalent, and we know that JISX equivalent will be in at 90 degrees with this ISR equivalent. So this is ISR equivalent, and JISX equivalent will be at 90 degrees with this vector. So we have three vectors, and after that we have to add all these three vectors using head to tail rule. And by adding all these three vectors, the Vp over A can be drawn from the tail of the first vector to the head of the last vector. So this is Vp over A. So clearly from this figure we can see that Vp over A vector is greater than Vs vector, or we can say the length of this vector is greater than the length of this Vs vector. So if we want to see the polarity of this voltage regulation, that is Vp over A minus Vs full load divided by Vp over A. So Vp over A vector is greater than Vs vector, so voltage regulation will be positive for a lagging power factor load. In the second case, I will show you how to draw the phasor diagram when we have a unity power factor load or a resistive load. So for a resistive load, again Vs is our reference vector, and Is will be in phase with Vs, and ISR equivalent will also be in phase with Vs. So this is ISR equivalent vector, and JISX equivalent will be at 90 degrees with ISR equivalent. And we can add these three vectors. So Vp over A will be drawn by joining the tail of the first vector with the head of the last vector. So again, in this case, the length of this VPA vector is greater than this VS vector. So again, voltage regulation will be positive for a resistive load or a unity power factor load. Now we are moving towards the load which is having a leading power factor, and that load is called a capacitive load. So again, Vs vector is our reference. Now Is is leading the Vs vector because we have a leading power factor load. So secondary current will be leading the secondary voltage, and ISR equivalent will also be in phase with IS, and JISX equivalent will be at 90 degrees with this ISR equivalent vector. So its orientation will be in this direction. And the sum of all these three vectors is Vp over A, which is starting from this point and ending at this point. So paradoxically, in this case, Vp over A is smaller than Vs because the length of this vector is slightly smaller than this Vs vector. So in this case, voltage regulation is negative. So we can say that for a capacitive load, only the voltage regulation will be negative, and for the resistive and the inductive loads, the voltage regulations are positive. So it means that for a capacitive load, if we have no load, we will get more voltage at the secondary terminals. But when we connect a capacitive load at the secondary, there will be even higher voltage as compared to the no load voltage for a capacitive load. On the other hand, if we have either a resistive load or an inductive load, the no load voltage will be higher, and as soon as we connect the resistive or an inductive load, the uh, voltage at the secondary terminals will start reducing. So this is how it works. So the transformer efficiency can be calculated by dividing the output power with the input power and multiplying their ratio with 100. So it will give us the percentage. And we can also write P out over P out plus P loss, because the input power is equal to the output power plus losses. So equivalent circuit has made efficiency calculations very easy. So if we can understand the equivalent circuit of a transformer efficiently, then the efficiency calculations will not be any big problem. So in transformer, there are several types of losses, and the first type of losses are called copper losses, and these losses are produced due to the resistance of the primary and the secondary windings. So these are also called I square R losses. And second types of losses are called core losses, and core losses are also called as iron losses, and they are also called as magnetic losses. So core losses has two types, hysteresis loss and eddy current loss. So both of these losses are the core losses. So in transformers, the output power can be calculated by this expression, and this is the expression for the active power, and efficiency can be calculated by dividing this output power with the sum of output powers and the core and copper losses. So transformer rating is always done in kVAs instead of kilowatts, because copper losses of a transformer depend on current and core losses depend on voltage. So total loss depends on the product of voltage and current, and this is independent of the load power factor. So now I am going to solve some simple problems, numerical problems, to get a deeper insight into the transformer calculations. So in this example, we have performed a no load test over a transformer, and the rated primary voltage of this specific transformer is 220 volts, and the rated secondary voltage is 110 volts. And under no loaded conditions, the primary current is zero point 0.5 amperes, and the power which is consumed at the input terminals or the at the primary of the transformer is 30 watts. So we have to first calculate the voltage transformation ratio or the turns ratio. So we have to calculate this resistive loss current, the current which is flowing through this resistor, and the current which is flowing through this inductance. So first of all, we will calculate the turn ratio, which is equal to V1 over V2, and this is equal to 2. The primary resistance, the resistance of the primary winding is given as zero point 0.6 ohms, and the power which is consumed under no load conditions is given by V1 I naught cos phi naught. So cos phi naught is equal to W over V1 I naught. So this is W, which is actually 30 watts, and 30 divided by 220 multiplied by 0.5. So this expression will give us the power factor, no load power factor, and it is calculated as 0.273. Similarly, we can calculate sin phi naught, and sin phi naught is equal to 1 minus cos square phi naught square root. So it will be given as 0.962. So now we can calculate this IW, and IW is equal to I naught cos phi naught, and we can calculate this I mu. It is given as I naught sin phi naught, and now we can calculate the copper losses, and copper losses are equal to I naught square R1, and I naught is actually the current which is flowing through this branch, and then that current actually diverts to this magnetization branch, and it is divided into IW and I mu. So for calculating the power, the copper losses, the I naught current must be considered. So I naught square into R1 is equal to 0.15 watts. These are the copper losses under no load conditions. And iron losses are equal to the total losses minus the copper losses. So total losses are 30 watts and copper losses are 0.15 watts. So iron losses are equal to 29.85 watts. So this is a no load test result, and we know that in open circuit test of a transformer, most of the power is consumed in this magnetization branch, and this magnetization branch actually corresponds to the core losses. So the power which is read by the wattmeter at the primary side will give us the core losses mainly, and in that case the copper losses are negligible. So this is what we have observed in these from these results. So the copper losses are 0.15 watts and iron losses are 29.85 watts. So most of the proportion of the losses in open circuit test are actually the core losses or iron losses. So now we are moving towards the second example, and in this second example, a transformer is given whose apparent power or whose kVA rating is 5. The primary rated voltage for a low voltage side rated voltage is 200 volts, and the rated voltage at the high voltage side are equal to 1000 volts, and the frequency is given as 50 hertz. So over this transformer, open circuit test and short circuit test both are performed independently. So first open circuit test is performed at the low voltage side, and the applied voltage is 200 volts. The current is read as 1.2 amperes and the power is read as 90 watts. Similarly, a short circuit test is performed, but this test is performed at the high voltage side, and in that case, 50 volts are applied at the high voltage side. The current was read as 5 amperes and the power was read as 110 watts. And the low voltage side was actually assumed as the secondary, and that low voltage side was short circuited. So calculate the parameters of equivalent circuit of the transformer referred to the low voltage side. So open circuit test will give us the magnetization branch parameters, and the short circuit test will give us the series resistance and the leakage reactance parameters. So the calculations are explained here now. So this is the first test, which is open circuit test performed at the low voltage side, and this is the high voltage, and the secondary side is open circuited. So this is the primary voltage, 200 volts is applied at the primary, and 1.2 amperes is the current which is observed, and the power is observed as 90 watts. So first of all, we will calculate the resistance of this magnetization branch, which is this R naught. And we know that when we have open circuit over here, then the parameters of this magnetization branch are much greater than the parameters of these series winding branch. So R1 plus JX1 is very less than R naught in parallel with JXM. So this branch can be neglected. So in that case, approximate equivalent circuit of this transformer will have this primary voltage and this magnetization branch. So from this circuit, R naught can be calculated as Vp square over P, because P is equal to V square over R. So we have this Vp, and we also have this power loss, which is 90 watts, and R naught can be calculated to be 444 ohms. Similarly, we have the primary voltage, we have this resistance, so we can calculate this current which is flowing through this resistance, and IR naught is equal to 0.45 amperes. So now we can calculate this current as well, and this current IMU can be calculated by using this expression, and 1.2 is the total ampere which is divided into this IR naught and IMU. So IMU will be equal to 1.2 square minus 0.45 square root. So this is equal to 1.11 ohms, and this magnetizing reactance in this case will be equal to the voltage divided by the current. So 200 divided by 1.11 is equal to 180.2 ohms. So these are the parameters of the magnetization branch, and we have to calculate all the parameters referred to the low voltage side. So open circuit test is already performed at the low voltage side, so we don't have to do any transformation with these calculated parameters. Now we are moving towards the short circuit test, which will provide us the values of these series resistance and leakage reactance components. But we have to remember that short circuit test is performed at the high voltage side, and these are the high voltage side parameters. And this low voltage side is actually short circuit in this case. So first we will calculate the total impedance, and that impedance will be equal to V over I. So V is 50, I is 5. So 10 ohm is the total impedance uh, refer to the high voltage side. And now we will calculate the resistance since we know this power. So this resistance will be equal to P over I square. So 110 divided by 25 is equal to 4.44 ohms. And now we will calculate this reactance, equivalent reactance referred to the high voltage side. This is the equivalent resistance referred to the high voltage side. So reactance will be equal to Z square minus R square and square root, and it is given as 8.9 ohm. So these are the parameters referred to the high voltage side. We have to transform these parameters to the low voltage side. So the low voltage side, we at low voltage side we have 200 volts. So we have to multiply this equivalent resistance with this transformation ratio. So 200 divided by 1000 square will be multiplied with this 4.4 to get this R1, and the same multiplication factor will be applied for this reactance to calculate X1. So these are the parameters which are referred to the low voltage side. So we have calculated all the parameters in equivalent circuit of a transformer. Now finally, this is the second part of the problem, and in this part we have to calculate the output secondary voltage when the transformer is delivering 3 kilowatts power at 0.85 power factor lagging. The input primary voltage is 200 volts, and we have to calculate the voltage regulation as well. So this is again the approximate equivalent circuit of the transformer referred to the low voltage side, and we have already calculated these parameters referred to the low voltage side, and the voltage at this low voltage side is a 200 volts. So first we will calculate the current which is flowing through this branch, this series branch, and for calculating this current we have to consider the information of the power and the voltage. So we know that I is equal to S over V. Okay, so since we know that S is equal to VI, S is the apparent power or the kVA, so I is equal to S over V, and S is equal to the apparent power, or S is equal to VI, and this is actually the active power. So the active power is equal to VI cos phi. So S will be equal to P divided by cos phi, and cos phi is our power factor which is 0.8. So we have to first convert this active power to the apparent power, and this active power divided by the power factor will be equal to the apparent power VI. So this will give us the apparent power, and we have to divide this apparent power with the voltage to get the current. So this is the current, which is the current referred to the low voltage side, and we have to now calculate the voltage drop in this circuit which is caused by this current. So if we multiply this current with this resistance and this reactance, we will calculate the voltage drop. So R1 cos phi plus X1 sin phi. These equivalent impedances will be multiplied with this current. This will give us the overall voltage drop. And to calculate the voltage regulation, we first have to calculate this voltage drop, and then we have to calculate, but then we have to divide this voltage drop with the no load voltage. So actually this voltage drop is giving us V no load minus V full load. So here we have V no load and here we have V full load, and their difference is actually giving the voltage drop across this series branch. So this voltage drop is calculated already, and we have to divide this voltage drop with this no load voltage or this primary voltage, which is 200 volts. So if I divide this with 200, then I will get the voltage regulation. So this is 6.69 volts divided by 200, and it is given as 3.345 voltage, 3.345%, the voltage regulation. So now we have to refer this voltage drop towards the high voltage side. Okay, so voltage drop is equal to 6.69 multiplied by 1000 divided by 200. So this transformation will refer this voltage drop or the voltage drop across this branch. So this voltage drop across this branch but refer to the high voltage side. So we have to multiply it by the 1000 and divide it by 200. So it will be 33.45 volts refer to the high voltage side. Now if we apply 200 volts at the primary side, and then we should have, ideally we should have obtained 1000 volts at the secondary, but when we subtract this voltage drop from 1000 volt, we will get actual voltage at the secondary. So 1000 minus 33.45 volts is equal to 966.55 volts, which is actually the secondary voltage, and it is slightly smaller than 1000 volts, which is corresponding to the voltage regulation. So voltage regulation is same. Either you calculate the voltage regulation at the low voltage side, or you calculate the voltage regulation for this high voltage side. The voltage regulation is always same. So that was all about our today's discussion, and I hope you have enjoyed and understood the concepts which are discussed in this lecture. So for watching more similar videos, please stay tuned to this YouTube channel. Until the next lecture, it's goodbye.